All right, in this problem, we have a ball that is released and rolls down a ramp 1 meter, and that takes 1 second. Then it's rolled and allowed to go for 2 seconds, and we want to find the difference between 1 second and 2 seconds. So to be able to find out how far it goes in 2 seconds, we need the acceleration. Well, we can get that from the first part of the problem. So if we do x equals v naught t plus 1/2 at squared, we know it went a meter, and we know it took a second. So we can get the acceleration. Then, if we go back to this formula, x equals v naught t plus 1/2 at squared, this time we know the acceleration, we just have to put in the 2 seconds. So it goes 4 meters. But the trick with this is it said from 1 second to 2 seconds. Well, in the first second it went a meter, in the second second it went 4 meters. So what was the difference from 1 second to 2 seconds? That would be 3 meters. In this question, they give you a velocity function of 4 plus 0.5 t squared, and they want to know what the acceleration is at 2 seconds. So what we're going to do is we're going to take the first derivative of velocity. So we're going to take the velocity derivative of this equation right here, and that's going to give us 2 times 0.5 is 1 times t. So the acceleration is just t. That 4 goes to 0. That just becomes t. Well, what's the acceleration at 2 seconds? That's just 2 meters per second squared. Now, this question is a little bit more involved. It says, what's the displacement of the object? So in this case, before we had the derivative of velocity gave us the acceleration. Now we need the integral of velocity to get the displacement. So we take the first integral of velocity with respect to time. So we set up our integral, and integrating 4 with respect to time becomes 4t. And integrating this, we add 1 to the new exponent and divide by that new exponent. And in fractional form, this becomes 0.167 t cubed. And then we have to take all of that from 0 to 6 seconds from our final and initial values. So plugging in the numbers, you get 60 meters for that. So let's look closely at this question. In the absence of air friction, an object near the surface of the Earth experiences a constant acceleration of about 9.8 meters per second squared. What is an acceleration of 9.8 meters per second squared? It means 9.8 meters per second every second. In other words, every second that goes by, it increases its velocity by 9.8 meters per second. So the answer is A. All right, let's take a look at this one. We have a 500 kilogram sports car. Now, because we're not using force in this problem, the 500 kilograms has nothing to do with it. Uniformly from rest, that means our initial velocity is 0, reaching a speed, that's going to be our final velocity. In 6 seconds, that's going to be our time. And the question is, how far did it go? Well, there's no kinematics equation that will let us do this in one step. So what we have to do is do a formula that gets us the acceleration. So since the initial velocity is 0, we can just plug in the 30 and the 6 to get us an acceleration of 5. Then we can do v naught t plus 1/2 at squared, and that's going to be 1/2 5 times 6 squared gives us 90 meters. Alternatively, we could have also said it went from rest up to 30, so that means it averaged 15 meters per second for 6 seconds. So we could have just done 15 times 6 to get the 90 meters. This question says we have an object shot straight up into the air with a positive velocity. So they've defined for us up as positive. Which of the following correctly describes the velocity and the acceleration at its maximum elevation? Well, when it gets to the top, it stops. so its velocity is 0. The acceleration is always in the direction of the net force. Well, the net force in this case is the force of gravity, and the force of gravity acts down, so its down is negative, so the acceleration is negative. In this one, they give you an equation for position as t cubed minus 6t squared plus 9t. And they want to know the net force on the locomotive is equal to 0 when t is equal to what? Now, we haven't done net forces yet. However, we know that when the net force is 0, the acceleration is 0. So all we have to do is find out what the time is when the acceleration is 0. The problem is they didn't give us a formula for acceleration. They gave us the formula for position. But acceleration is the second derivative of position. Or we could say, take the derivative of position, then take the derivative of velocity to get the formula for acceleration. So the first derivative of this, we use the power rule, gives us 3t squared minus 12t plus 9. And then we take the derivative of this, giving us 6t minus 12. All we have to do now is set that equal to 0. So we bring the 12 to the other side, and we have solving 12 equals 6t, and t comes out to 2 seconds. All right, we have an object that's dropped from rest. That tells us the initial velocity is 0. From the top of a cliff that's 400 meters. So this is kind of tricky information because it says, what is the distance the object travels during the first 6 seconds of the fall? It never says that the ball falls 400 meters. So this information is not x. X is actually unknown. So what else do we know? The acceleration is 9.8, the time is 6 seconds, and we're looking for x. So once you realize that that's not given information, this is actually an easy problem. It's just 1/2 at squared. In this equation, we have a position given as 3t squared plus 1.5t plus 4.5. And it says, what's the instantaneous acceleration of the object at 3 seconds? So just like the problem that we did 2 problems ago, we're given a position formula, but we want an acceleration formula. So what we need to do is take the first derivative of position to get velocity. So the first derivative of this gives us this, and then we take the derivative of velocity to get us acceleration. And acceleration is 6 meters per second squared. Notice there's no time in there. So the question was, what's the acceleration at 3 seconds? Well, it's 6 meters per second squared the entire time. So it's 6 meters per second squared at 3 seconds. It's also 6 meters per second squared all the time. This question is very tricky. And the way that I ended up solving this was to call up to be positive, and then to call the origin of the problem the ground. So the ground is 0 meters. So this ball is at height h, whereas this ball is at height 0. So they want us to get an answer for time in terms of h and v naught. So let me show you how I did this. What I did was I made an equation for the dropped ball and an equation for the launched ball. For the dropped ball, we know the height is h, 1/2 gt squared. But if you notice, g is not in any of the answers, so we need to get rid of g somehow. So what I did was I wrote the equation for the launched ball. Now, because our origin was the ground, the launched ball starts at 0 meters, so its position is 0. Then we say the initial velocity times time minus gravity, which is down, negative. And then we can solve for g. Then all we have to do is take that g and substitute it in, and we get 2 v naught over t. One of our t's cancels, and the 2's cancel, and we're left with t equals h over v naught.